those are two oxidations. We could fully oxidize an alpha carbon to make a benzoic acid. We can make a carbon-bromine bond at the alpha position. Let's talk about reduction. Benzene rings, because benzene is so stable itself, normal compounds that reduce double bonds will leave benzene untouched. So if I have this compound 4-phenyl 3-butene 2-one, here, I'll number this for you. 4-carbon compound, carbonyl C double bond O and carbon 2 double bond on 3 and 4, and a benzene ring attached to carbon 4. So if I react that with hydrogen and palladium, palladium is the catalyst. It's the metal catalyst that allows us to add hydrogens to things like double bonds. What will happen here is that we'll be able to reduce this one double bond that's outside of the benzene ring. So there's one hydrogen on each of those double bonded carbons. Now, in the product, we've removed the double bond by adding H2 across the double bond. The double bond is reduced. Normal carbonyl groups that are just on an alkyl side chain are unreactive to catalytic hydrogenation, as is the benzene ring. So in this case, the only thing that was reduced was just that double bond there. However, carbonyl groups next to a benzene ring, or using our terminology, carbonyl groups that are alpha to a benzene ring, are reduced by hydrogen and palladium. That's because, remember, I told you the alpha position is more reactive than other carbons. What this does for us is lets us get around one of the main limitations that Friedel-Crafts alkylation posed to us. Let's look at this bottom pathway here first. If I have benzene and I add 1-chloropropane with aluminum chloride, what we're attempting to do here is to make a N-propyl carbocation, which is primary. And remember what we said primary carbocations do? They undergo a hydride shift. And we'll actually have one of these hydrogens shift over to make a secondary carbocation. So the N-propyl carbocation became an isopropyl carbocation. So if I just tried to use N-propyl chloride to add an alkyl group, we would get a mixture of N-propyl benzene as well as isopropyl benzene. We cannot reliably get a good yield of the product we're looking at because of carbocation rearrangement. Okay, so that path is not feasible to us. What we can do, however, is add this compound with 3 carbons, a C double bond O, and a Cl. It's called an acid chloride. We have a whole chapter on them later, but we'll do in Friedel-Crafts acylation, because remember that acyl cation is resonance stabilized with the oxygen lone pairs next to it. Okay? There is no rearrangement with acylation, so I can reliably make this 3-carbon side chain, although it has a CO double bond. But since that's on the alpha carbon, I can use hydrogen and palladium to reduce that CO double bond. Okay? What we'll get is just regular old propylbenzene through reduction right there, the product we were trying to get with alkylation, but we can now get in excellent yield. So if I have a alkyl group which is prone to rearrangement, right, where, for instance, if I want to have a primary carbon attached to the benzene ring, or really any other kind of complicated alkyl group, the best way to do it is by an acylation first, and then a reduction. So the other useful thing about this is I can control whether a group I have on a ring is a metadirector or an orthopara-director. This propiophenone here, the carbonyl-containing compound, is a metadirector, because it has a C double bond O next to the ring. However, after I reduce it, it becomes an orthopara-director, propylbenzene, because it's just an alkyl group. So depending on when I do this reduction in a sequence of steps, I can get groups to add either meta to it or para-ortho to it. Okay? So we'll take advantage of that in our synthesis. One more useful thing is that nitro groups. Here is a nitro group, NO2. Nitro groups are reduced to amines, okay, to NH2 by that same reagent, by hydrogen and palladium. Our book mentioned a different reagent for that, but it works just fine with hydrogen and palladium, so why not just remember that one, that reagent, as a reducing agent. So if I have a nitro group that I want to become an amine, I can use hydrogen and palladium. That is handy because that also turns a meta-director into an ortho-para-director. You have to be careful what else is present, because any carbonyl groups that are alpha to the ring will also be reduced. So if you have a compound with a nitro and a C double bond O next to the ring like that, they'll become respectively an amine and just a regular alkyl group.